Hi, Isaac. Hope you feel better. He's sick today at home. So everybody say, I hope you get better, Isaac.
Hope you get better, Isaac.
Sweet. That was
Get
so
well
good.
soon.
So, this is a numerical technique for approximating a zero of a function with a zero of its linearization. That's right, linearization. Linearization. Okay? So it's a numerical technique for approximating a zero function with a zero of its linearization. It's going to be another one of those formulas. You're going to have to get down just to learn a little bit about it. Thankfully, though, it does have to do with linearization, which is a formula that you already all learned. So, the first step for Newton's method is we need to guess the first approximation to a solution. So first we need to guess the first approximation. We want to guess, okay, well, where does f of x equal 0? At what x value does the graph equal 0? In order to do this, a lot of the times you're going to use your graph. You look at the graph and consider, okay, well, where does this hit 0? If it's not a rational or real number, if it's irrational, and we can't factor it, we don't always have the tools to factor it, we can use Newton's method to guesstimate them. Okay? So, once we have our first approximation, what we're going to do is then we are going to use that first approximation with Newton's method and guess again. We will continue to guess with our approximations, using our approximations to find out, okay, well, what is the closest I can get? So, step number 2 is to use the first approximation to get a second, to get a third, and so on, using, and here is going to be Newton's method's formula. It is going to be that your approximation of the next value you're guessing is going to be equal to the last number minus the function at the value divided by the function's derivative at the value as well. Great question, no clue. So this is saying x sub n plus 1 equals x sub n minus f of x sub n divided by the derivative of f of x sub n. So basically, this number right here is our guess. We're going to use this to guess, right?
Oh, okay.
Then that guess, we're going to input it into the function itself, and then we're going to input it into the derivative. And we subtract that, and that gives us our next number. Well then, we're going to put that number right back in here. And then we're going to put that number back in here, and find the next one. And then we're going to continue to do that until we reach what we believe is a good 0. And I will show you how to find out, do we think that's a good 0 or not? Now, this is really cool because do y'all remember last year when we were doing synthetic division and breaking polynomials apart?
Yes.
And we had to really like guess and figure out what do I divide by, what hints can I use and such. However, that only works when we have real solutions. What if you have a function that's like a 6th power polynomial with no real solutions? What would you do then? Well, you could use Newton's method. Okay? So let's go ahead and try this out. We have x cubed plus 3x plus 1 is equal to 0. So everybody, first things first, you should always go ahead and graph it in your calculator. Oops, someone was,
Oh, do we have a progress check tomorrow?
I might do like a worksheet thing instead.
That
Maybe.
sounds good.
Have it due on Thursday, and then that way it's not, because Newton's method and linearization is something I definitely want to test on, but not necessarily Newton's method as much. We do use it again, but it's one of those more nuanced things that you can use, but you don't need to use. Okay, so when you graphed it, you should have graphed it. It looks something like. I really need to finish graphing it.
Do we include the equal 0 or no?
No, because that's just what we're trying to solve for. So that is just us trying to find out where the 0 is. You just imagine that it's still at that's still the y. Oh my goodness! X plus 3 plus 3x plus 1. Graph it. We good. All right. So our graph looks something like. Does your graph look like this? Like so? And it looks like it's a little bit before 1, right there, okay? So what I'm going to do is I'm going to go ahead and I'm going to guess at negative 0.3. So I'm going to go ahead and guess at negative 0.3, but first I have to take my derivative, which equals 3x squared plus 3. And then with Newton's method, I know that x of n plus 1. So I want to find out what my x of n plus 1 is. Or really, I want to find out what value to look for. This is going to be equal to x sub n minus, then we get x sub n cubed plus 3x sub n plus 1 all over 3x sub n squared plus 3. Why would you plus 1? Because that's the function. I'm just inputting a value in for the function.
What does the sub n mean?
Sub n?
Yeah.
That just means it's assigned a value right there. So like x sub n, so like if x sub n, if n equals 1, that's x1. If x equals 2, then if n equals 2, then that's x2. It's just a way to linearize, kind of like do a, like here's x1, here's x2, here's x3. It's just to order our guesses, right? So let's go ahead and approximate these. We're going to get that x1 is equal to, what should we guess first?
Do x1
Huh?
Why did you do x1?
Well, no, first we have to guess. So what's our guess going to be? Everybody look at your graph, maybe zoom in a little bit. I'm going to say my 0, I'm going to guess that it's at negative 0.3. I'm just going to make a guess there. I'm going to say, no, shut up. Don't just give it away like that. That's rude, Cody. That's so rude. Stop that. So we get x1 equals negative 0.3. All right, awesome. Therefore, x2 is going to equal negative 0.3 squared minus negative 0.3. Sorry, this is just, sorry, no, oops, my apologies. This is just negative 0.3 minus parentheses negative 0.3 cubed plus 3 times negative 0.3 plus 1 is, and then divide that by negative 0.3 squared plus 3. There we go. Okay.
How did you get that if you're trying to use the derivative? Isn't it 3x?
Oh, what? Oh, yeah, sorry, times 3 on the outside. Correct.
So how are you supposed to make a guess without the graph?
You just have to guess. No, you will always have to guess with the graph.
So
It's just going to tell you use Newton's method.
So you like, oh, I got a graph.
Okay. So now, what do you do with this? Calculate out by hand, obviously, right? Let's get started. I'm just kidding. Just stick that in your calculator, shell. This is Newton's method is not a no calculator thing. It is a calculator kind of thing. And also, don't try to put it in. Try to see if you can put it in one. Yes. Question.
They didn't really have
Good. So what we're doing is using Newton's method. We're getting closer and closer to zeros. The idea, we'll see. You will see a little bit of a visual of it, and I'll see. There's a pretty cool video I'll pull up. But the idea is basically we have this right here. This is, let's say we have this function here. We don't know what that is, right? But I'm going to guess a 0 here at this point. Well, what point does that line up with? This right here. So therefore, I'm going to get this point here. And then as you do this, your guesses are going to start getting closer and closer and closer and closer. The math behind this is a lot more complex, but the whole point of this is that we're guessing a 0. Using Newton's method, it gives us a new one. Then we use that one, and it gives us another 0, and another one, and another one, until we get close enough. Yes, Emma? Oh, that's great.
Why is my calculator? It's like on.
Oh, you are in the wrong mode, right? Wait.
Why is it not the same?
I think yours is right.
I did negative. Oh, I did negative 3 once.
There we go.
So why do you X up to
I got closer to 0.
That's way too far.
Oh, I
Like you want to guess. You want to guess with these you want to guess decimal numbers. Catherine, question?
So are you guessing what you think it is, or something really close to this?
What you think? No, you're guessing really, really like it's not negative 0.3 because we know it's rational. We don't know what it is right now. So I'm just guessing negative 0.3 because it could be negative 0.3. So your answer here, you should have gotten negative 0.3223224 1, 5, and 9. Now,
That's what you calculate your delta. That's what you do when you do second tracing the graph.
you don't get that value of second trace in the graph. You get very, very close to that. Let me see. Did something happen around here? Did anyone else get the same thing I did?
Yeah, I did.
What?
I got 3,
Why did I get it
2,
wrong?
6, 7. What? I got the exact
I
same.
got the
exact same thing.
Oh, to go further on and on and on. I would say try again, but what's going
All
on
the
here?
same. That's what mine did. It was 1 for.
Wait, what did you get?
He got 0.02.
That's what I got.
I
I plugged in the exact same.
Are you sure?
Radian
It doesn't matter.
effect
Yep.
multiplication.
Try again, just clear it out, and then just input it again. Maybe try top and bottom. So now, what we need to do, and this is going to be important, everybody. This is going to be important. I want you to store this into your x value. So everybody play stow x. Stow x. Because now, what we are going to do is find our x3. So, to find our x3, we use the same thing, but now, what can I just put in my calculator? I can just put this formula in. The x of n should just be x's. So you can put in a polynomial in there.
Same thing. I got 3.
Yeah. Negative 0.2.
You should try calculating it.
What just happened?
Like doing it number for number.
I don't know.
So you do negative
I keep getting the
0.3,
same exact thing.
power of 3
What are you getting?
plus
Same thing you're
3.
getting.
0.02232. Why is it like that, bro?
Dog, I don't even know. Freaking weird calculator.
Bro, I keep getting the same thing.
Grant does too.
I'm going.
No.
I got it. Yeah.
Just don't even.
I'm trying to do Oh, very good. What are you getting, Mr.
Wow, I got to send the unit actually.
What?
Oh, I see. You forgot to put. What did you forget at the front?
Oh my goodness gracious.
There's a negative 0.3 in the front, everybody. That's why you keep getting it wrong. Okay, we can move on now. I've fixed it.
I got it too now.
So now, this is what you should be putting into your calculator. You should put in negative 0.3 minus x cubed plus 3x plus 1 over 3 parentheses, 3 times x squared plus 3. And if you do this with storing x, I will have you practice this once. Go ahead and do so. You should have gotten, you just click stow x once you get your answer. Stow should be right under natural log.
Stow.
Now you need to use, oh yeah, so this now, sorry, this changes into, sorry everybody, you're correct. That is x, right there. Yes, you're correct. Thank you. You should have gotten, just so that you know, you will get negative 0.322185363.
Wait, why does the negative 0.3 become
Oh, because remember that we have to, every time we do this, we replace our x with the next x.
Okay.
So once we get our x sub n, we then change it. What does x sub n plus 1 become? It becomes x sub n. And the new x sub n plus 1 is what we're trying to find. So therefore this goes here, 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 and here.
So that negative 0.3223.
Yeah, so that number goes right there. Okay, and then you should get x4 equals. Negative 0.3221. What do you get? 8 again. Then 5, 3, 5, 4, 6. Now, this is where we can finally stop once we get to this point. The reasoning for that is I want you to go ahead and look at these decimals here. Do you notice something about the first 4 decimals? We have 4 decimals here that are the same. When you're doing this, look for 4 similar digits. So once you hit those 4 similar digits, you are good to go. Yes, Caleb.
Just for clarification, on the third step, you plugged in the second step's value into the x, and then on the fourth step, you plugged in the third
Yes,
step's
you just
value
keep
into
using
x.
that x sub n to find new ones, 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 until you get to the point where you notice now it's not changing as much anymore, right? At first we had a pretty big change from 0.2 here. We changed from 2.3 to 2.1, which doesn't seem big, but it is big. Then this changed only to 2.1. We don't care about all the little ones. Once we get this close, we're good. Yes.
What were you talking about with the store x thing?
Oh, so instead of having to rewrite this, whenever you get an answer, so like here's your answer, right? You just click stow and then hit X. And now whenever you type in X, what happens? You get that number. So now you can just use the format I have up here. If you put this into your calculator now, you will get this answer that you just store X, same thing, store X, same thing. You don't even have to type this out. The nice thing about that is this will just continuously do it for you. Okay? You just stow something else. It doesn't matter. Okay. So let's go ahead and. Do I want to do this one?
Yes.
Really? Yes, Catherine?
Do you have to input the equation with just the x's into the y equals and then you can like do y1 x thing? I don't know.
How do you mean?
Because you stored it and now what do you do with this?
So now you input this into your calculator with the x's. So x minus x cubed plus 3x plus 1 divided by that. And then the nice thing about that is once you finish that, you click store x, go back up there, hit it again, it'll calculate it out. So really, once you do, the first one is really slow, right? It takes a while to do the first one, but once you do the first one, the second, third, and fourth, they get super easy as long as you do the correct format on here. So if you need help with your calculators today, let me know. We're going to skip over the exploration for a moment. And let's go ahead and talk about differentials. Okay? So, the first thing we're going to do, and differentials are nice and simple, because all we really do is we take the derivative, and then the differentials, as we recall, I separated out dy and dx, right? Because remember, what is dy over dx for? The change in y over the change in x. So therefore, right now, if we know what the change in x is, and we just want to find the change in y, we can use just our dy and dx. So, recall whenever we take the derivative of a variable, we always have to replace that with dy or dx or dt or whatever it is. So here, what is the derivative of x to the 5th plus 2x?
5x to the 4th.
Very nice. So we should get dy is over dx is equal to 5x to the 4th plus 2. Well, what we are trying to do is we're solving for dy. We want to find the differential dy and evaluate dy for the given value of x. So therefore, what do I need to get rid of over here? What do I not want anymore? I don't want that dx. So multiply by dx on both sides. We're going to get dy is equal to, parentheses, 5x to the 4th plus 2 dx. Then we want to evaluate this at two places. The first is going to be at x equals, what is the value there? Is that 1? Yep. And dx is equal to 0.01. So therefore, we are going to get dy equals 5 times 1 to the 4th plus 2 all times 0.01. So we should get 5 plus 2 is 7 times 0.01. The differential, when x increases by 0.01, how much is dy going to increase by at the point x? It's going to be 0.07. This is basically kind of like finding the slope of the tangent line you created, but just how much the y changes as the x changes by a certain amount. Okay. Any questions on that? How to find differentials? Yes, Catherine?
So what are we doing and why are we doing it?
So for this one,
I like that question.
that is a good question. Let's go on to the next problem, and that will answer your question, actually. Yep. See, I love those questions because nobody, everybody in my Algebra 2 class always asks me, why are we doing this? Why would we do math in the first place?
That's a good
And Catherine asked me these questions, and now I'm like, well, I guess I know what I'm doing tonight. I'm going to Google all these problems and be like, all right, why do we do these? What are the high level, because a lot of the times whenever I Google this stuff, it's like, well, you don't use Newton's method until you reach linear algebra, which is past Calc 3, and then once you hit that point, you're not going to use it again until you hit an engineering specific problem, which only if you follow the course of engineering, which is why calculus can be frustrating for some people, because you learn a lot of cool stuff, but you learn a lot of stuff that you have to learn if you're going in an engineering track, which I'm assuming not everybody here is going engineering. Probably not. So let's go ahead and look at this. The radius of a circle is increased from 5 to 5.1 centimeters. Estimate the resulting change in area, and then express the estimate as a percentage of the circle's original area. So let's go ahead and start with this. What is the radius of a circle? So the radius of a circle is increased from 5 to 5.1. Estimate the resulting change in area. So what is the formula we are looking at right now? We are looking at area of a circle. So A equals pi r squared. Very good. Then we also get, we take the derivative, and what is our derivative going to be? It's not dy over dx. It should be, what's the derivative of the left side? The derivative of A is, and the derivative of r is dr. It's always going to be whatever's alone, and then whatever is on the other side, equals 2 pi r. Okay? And it wants us to find out, how much did the radius of the circle change from? The radius of the circle increased from 5 to 5.1. So therefore, how much incrementally did I increase by? 0.1. So therefore, I know that my dr is going to equal 0.1. And then what should my radius equal? Well, I want to find out about express the estimate as a percentage of the original area, so I'm going to use 5 right here, so I get that, so I'm going to say that the radius is equal to 5. So now I get dA equals 2 pi r dr, or dA equals 2 pi times the radius, which is 5, times 0.1, which is the same as 10 pi times 0.1, which is equal to just pi. Okay. So how much did our area change? When dr changed by 0.1, when the radius changed by 0.1, how much did the area change by? It changed by pi, right? So, does that make sense now, Catherine, what we did there?
Yeah.
So we looked at, if I change the radius, how much is the area going to change by? This differentials is how we do that, which is pretty cool, because remember when we used to do squares, and we used to look at a square and be like, okay, well, if we increase the side of the square by 2, therefore shouldn't the area increase by 2? No, it's going to increase by 4, because you have to add 2 twice, and you use the area twice. With this, you don't need to use kind of that knowledge. If you just do regular, if you use this method, you will get the correct value of, well, oh, it increased by this much instead of that much. Because this kind of takes into account adding it to 2 sides because of the derivative. It's a little bit hard to see. But now our last step is, well, how much did it change? What was the percent change? What is our original area? What is pi r squared with a radius of 5? You should get 25 pi. And what's the new change? The change of the radius, the change of the area is pi, which is 1 over 25, or 4 over 100, or 4%.
What was that last step? Why did you put it
So
on?
this right here, it asks you to estimate as a percentage of the circle's original area, right? So therefore, how much did the area change of the circle? It changed by pi, right?
Yeah.
And then how much was it originally?
Okay.
So we're looking at the change over the original. So it changed by, how much did the circle's area increase by when we increase? If we increase the radius by 0.1, we know it increases by pi, and we know it increases by 4%. Okay?
Where'd you get 25?
25 pi, that's the original right here. What's the area of the circle in the first place? The radius is 5, so what's pi times 5 squared? 25 pi. All right. Any more questions on this one?
No, this makes sense.
We're getting into the topics where it's harder for me to just show you kind of like the generation of them. Like if you recall, we had all those times with sine and cosine where I could show you how we developed the derivatives and such. But now we're up to here, and at this point, it's getting into the Calc BC and higher topics, and it's harder to show those without having Calc 3 background and so on and so forth. But for now, let's go ahead and get to the homework. Oh, that was a good turn. I just turned straight to the homework page. You're going to be doing 7 through 9. And, I love that, 11 through 15. And
That's it.
17 through 21. With 17 through 21, try to get to those. If the I really want you to focus in on these first 6 though, or maybe is it 7? 11, 12, 13, 14, 15. Yeah, 7 or 8. Besides that, you are good to start working. Yes, we did. I know, it's weird seeing her But it's nice that I don't have to work in the hallways anymore. Just because it's working in the hallways is rough, isn't it?
You literally just did it.
Plus, I mean, you don't like. I got the nice thing about it though is I got to talk to a lot of teachers. Like especially my first year here, I just would be in the hallway and someone would stop by and be like, "Oh, hey, Mr. Holmes," and then I would chat. Huh?
Oh, is that what
Some periods are annoying.
You know what I mean? Yeah, you got,
No, I'm just kidding. It was mostly because I was printing a lot, so I felt really bad about like running in and out of the room. So I'm like, if I'm just gonna work, why not work in the hallway and then print everything, get everything finished, and then run back inside once I have everything done. But most of the time, I just end up working in the hallways. It was easier. So when you turn off the video for Isaac, because I do not edit any of this. Ain't no way.